let's see how we go.
I'll share it on social media if you want to. Share your YouTube channel.
Keep talking.
Oh, is it on?
All right, so we're going to look at the conical pendulum, which is just another application of motion of a particle in a circle. So the difference here is that instead of operating on a table or on the ground, we've got a weight that's attached to a string, and the string's attached to a roof or above somehow, and then we're spinning the object around. So it's travelling in a circle, a horizontal circle, but it's attached by a string to the roof.
So instead of it the other way being attached to the horizontal, now it's attached to the vertical.
Yeah, so we looked before, we had like a table, we had a point in the middle of the table,
yeah,
a string to the object, and we just had it circulating on a horizontal platform. Still the circle here is horizontal, but we just connected it to the roof. So we again need to resolve the forces that are acting on the mass to keep it in its circular motion, and then once we resolve them, we apply Newton's laws to get expressions for the things we need to find. So we've still got gravity acting down, so that's our mg coming down, acting straight down on the particle. But then instead of having a physical connection to the middle of the circle, we've got tension that's acting back up this way towards the roof that's holding it in its circular motion. Okay. So we're going to need to resolve the forces vertically and horizontally, so we can find out the different unknowns that we need to find out going forward. So basically what we do is we draw a triangle here, and the angle down the bottom here will be the same as the semi-vertical angle of the cone. So this is going to be theta in here. And then we can have the horizontal component of the tension and the vertical component of the tension that we can then resolve against gravity pulling down on the object. Okay, so we've got for the tension, horizontally, so you might call this TH, is going to be T sine theta, and vertically we've got T cos theta. Okay? So once we have those two components of the tension, we can then apply that with the force due to gravity to work out exactly where the particle is going to hold. So horizontally we can say that, bigger, that the horizontal component of the tension has to be equal to the resultant force on the particle, which is mv squared on r, and the vertical component of the tension must be the same as gravity acting on the object, so that it stays in the same horizontal plane as it rotates. Okay, so tension on the string is the only force that's acting upwards, and gravity is the only force acting downwards. So we just resolve those two forces. Okay, you good so far? So we'll look at an example, and I'll show you how it works. And hopefully, then you can do some on your own. So we've got a light string OP fixed at the end O to a roof or something, and the particle P is on the other end. It's moving in a horizontal circle. The centre of the circle C is directly below O and a distance h from it. Prove that the period of motion is given by the expression 2 pi times the square root of h over g. And in part 2, if the number of revolutions per second is increased from 1 to 2, find the rise in the level of the circle. Okay, so we'll do the first one first. And remember, what's the formula for period?
2 pi on n.
2 pi on, for this we're going to say omega. Okay, the angular velocity, yeah?
Yeah.
2 pi on omega. So basically, we need to find out what omega is to be able to find out what the period of the motion is. Okay, so we'll start off with our two equations. So we've got horizontally that T Sine theta is equal to mv squared on r, or mr omega squared. They're both the same expression, yeah? And t cos theta equals mg, acceleration due to gravity, or force out of gravity. So what I'm going to do is I'm going to divide these two out. Okay? So if I divide them,
So you get T tan theta.
the t's will cancel, yeah?
Yeah, so you get tan theta equals
I get tan theta
R omega on G.
gives me r omega squared on g. Okay, which is great. We're on our way. From our diagram here, we're told that this distance from where it's connected here at O down to the centre of motion C is h, and we're also told that the radius of motion is going to be r. So we can say there that tan theta will be what?
R on H.
R on H. So we can say since tan theta equals R on H, we can have R on H equals R omega squared on G.
That'll cancel nicely.
Okay? So the R's cancel out, or we can divide the R's out, and then we've got omega squared, omega squared equals G on H, and that gives us that omega equals the square root of G on H. And obviously we take the positive square root because we need the velocity to be positive in this instance. Therefore the period is going to equal 2 pi over that, which gives me 2 pi times H over G, which is what we require. Okay, so that was part 1. I might give you a chance to copy that down and I'll do part 2 for you. Yeah?